Where did all the energy go? Our universe, vast and seemingly infinite, is missing a significant chunk of its energy, a cosmic enigma that has baffled scientists for decades. We're not talking about a small discrepancy. It's a colossal amount, and the question is why we can't find it. This missing energy has led to some mind-bending theories, with scientists proposing everything from hidden dimensions to entirely new forms of energy and matter. In this video, we're diving deep into the heart of this mystery, exploring 30 fascinating theories that attempt to explain the universe's missing energy. We'll uncover the concepts of dark energy and dark matter, the invisible entities that make up the majority of our cosmos, and we'll explore how these concepts might hold the key to understanding where all the energy went. From quantum fluctuations in empty space to the possibility of parallel universes, prepare to embark on a journey through some of the most cutting-edge and mind-blowing ideas in modern astronomy. Join us as we unravel this cosmic puzzle, sparking your curiosity and inviting you to ponder the profound mysteries of the universe. First, we'll explore the quantum vacuum energy theory and see how the concept of emptiness isn't really empty. Looking into the very fabric of space itself, we encounter quantum vacuum energy. According to quantum mechanics, what we perceive as empty space is anything but. It's actually teeming with virtual particles that are constantly popping in and out of existence. These particles, though fleeting, possess energy, contributing to what's known as zero-point energy. This concept suggests that even in the absence of matter or radiation, space is filled with fluctuating energy fields. The idea that quantum vacuum energy might account for the universe's missing energy is intriguing. After all, if space is inherently energetic, it could explain the accelerating expansion of the universe without requiring exotic forms of dark energy. However, there's a significant problem. Our calculations of the amount of zero-point energy in the universe are vastly different from what we observe. The theoretical amount of vacuum energy is many orders of magnitude larger than what's needed to explain the observed expansion. This discrepancy is one of the biggest unsolved problems in physics. It's like trying to balance a checkbook where the numbers are off by a factor of trillions. So, what's going on? One possible explanation involves the cosmological constant, a term introduced by Albert Einstein into his theory of general relativity to counterbalance gravity and create a static universe. When it was discovered that the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. However, the concept has been revived as a possible explanation for dark energy, with the vacuum energy acting as a sort of cosmological constant. Despite its potential, the cosmological constant faces the same issue as vacuum energy. The predicted value is way off from observations. Scientists are still grappling with this puzzle, exploring various ways to reconcile theory with reality. Could there be some unknown mechanism that suppresses the vacuum energy? Or are we missing something fundamental in our understanding of quantum mechanics and gravity? It is time to move on to the next potential answer to the mysterious energy. Transitioning from the static nature of the cosmological constant, let's explore another intriguing possibility, the quintessence field. Unlike the cosmological constant, which is constant and uniform throughout space, quintessence is envisioned as a dynamic, evolving energy field that permeates the cosmos. The term quintessence comes from ancient Greek philosophy, referring to a fifth element beyond the traditional four of earth, air, fire, and water. In cosmology, it represents a similarly ethereal and pervasive presence. One of the key distinctions between quintessence and the cosmological constant lies in its behavior over time. While the cosmological constant remains unchanged, quintessence can vary, its density and pressure evolving as the universe expands. This dynamic nature offers a potential solution to some of the problems associated with the cosmological constant, such as the fine-tuning problem. The fine-tuning problem arises from the extreme precision required in the initial conditions of the universe for the cosmological constant to have its observed value. Quintessence, with its evolving properties, could alleviate this issue by naturally adjusting to its current state over cosmic time. The appeal of quintessence lies in its ability to explain the accelerating expansion of the universe while accommodating a wider range of possibilities. It opens the door to models where the dark energy density changes over time, potentially leading to observable differences in the expansion rate at different epochs. However, quintessence remains a hypothetical concept. Its existence has not been directly confirmed, and its properties are still largely unknown. Scientists are actively searching for evidence of quintessence through various observational techniques, such as studying the cosmic microwave background and mapping the distribution of galaxies in the universe. These observations could reveal subtle variations in the expansion rate that would distinguish quintessence from a constant cosmological constant. The search for quintessence is an ongoing quest, pushing the boundaries of our understanding of the universe. As we probe deeper into the cosmos, we may one day uncover the true nature of this elusive energy field. Now, leaving behind the idea of dynamic energy fields, we will look at a theory that negates the need for dark energy altogether. The third theory involves modified Newtonian dynamics, often called MOND. This approach dares to challenge the very foundations of our understanding of gravity. MOND was initially proposed by physicist Mordechai Milgrom in the 1980s as an alternative to dark matter. Instead of postulating the existence of unseen matter to explain the observed rotational curves of galaxies, MOND suggests that Newton's laws of gravity break down at very small accelerations, such as those experienced by stars at the outer edges of galaxies. This modification introduces a new fundamental constant with the dimensions of acceleration, below which Newtonian dynamics no longer hold true. At these galactic scales, the gravitational force becomes stronger than what Newtonian physics predicts, allowing stars to orbit faster without requiring the presence of additional dark matter. One of the primary reasons some scientists favor MOND is its remarkable success in predicting the rotational curves of galaxies. In many cases, MOND accurately matches the observed velocities of stars based solely on the visible matter in a galaxy, without the need for any fitting parameters associated with dark matter halos. Additionally, MOND elegantly explains certain empirical relations observed in galaxies, such as the Tully-Fisher relation, which links a galaxy's luminosity to its rotational speed. However, MOND is not without its challenges. While it performs well at galactic scales, it struggles to explain phenomena at larger cosmological scales, such as the cosmic microwave background and the large-scale structure of the universe. Observations of galaxy cluster collisions like the Bullet cluster also present difficulties for MOND, as they seem to indicate a separation of gravitational lensing effects from the visible matter, something more naturally explained by dark matter. Furthermore, MOND lacks a complete theoretical framework that can consistently incorporate it into general relativity, though ongoing efforts are attempting to address this. The debate between MOND and dark matter continues, with both sides actively seeking new evidence to support their respective theories. While MOND offers an intriguing alternative that eliminates the need for dark energy by tweaking the laws of gravity, our next theory explores an even more radical possibility: phantom energy. Transitioning from modifications to gravity, the fourth theory considers an even more outlandish proposal: phantom energy. This concept takes the properties of dark energy to an extreme, suggesting a form of energy so potent that it could ultimately rip the universe apart. Phantom energy is characterized by an equation of state where the ratio of pressure to density is less than -1, a property that sets it apart from other forms of dark energy, including the cosmological constant and quintessence. This peculiar characteristic implies that as the universe expands, the density of phantom energy actually increases, leading to a continuously accelerating expansion. As phantom energy dominates the cosmos, its repulsive force grows ever stronger. Initially, this increased expansion might only affect the largest structures, causing galaxy clusters to drift apart at an accelerated rate. Over time, the effects would intensify, eventually overcoming the gravitational forces holding individual galaxies together, tearing them asunder. Stars within these galaxies would then become unbound, and planetary systems would disintegrate. The escalation continues until phantom energy becomes so overwhelming that it even overpowers the electromagnetic forces holding atoms together, leading to the ultimate destruction of all matter. This cataclysmic scenario is what scientists refer to as the Big Rip. The speculative nature of phantom energy stems from its reliance on exotic physics and its potential violation of fundamental energy conditions. While current observations do not definitively rule it out, they do place stringent constraints on its properties. The implications of phantom energy for the universe's fate are profound. If it exists and continues to dominate, the universe is destined for a violent end, quite different from the more gradual heat death predicted by other dark energy models. The Big Rip poses significant theoretical challenges, as it implies a future singularity where the laws of physics, as we currently understand them, break down. Considering such a dramatic end, our exploration now shifts to another intriguing possibility: the idea of cosmic strings and topological defects. Venturing beyond the exotic realm of phantom energy, the fifth theory turns our attention to the very fabric of spacetime and the potential for defects within it to account for the universe's missing energy. These defects, known as cosmic strings and topological defects, are hypothetical remnants from the early universe. They represent flaws in the structure of spacetime that could harbor vast amounts of energy. Cosmic strings are one-dimensional objects, incredibly thin but immensely dense, thought to have formed during phase transitions in the early universe, analogous to cracks that form when water freezes into ice. These strings possess immense gravitational pull, potentially influencing the distribution of matter and the expansion of the universe. Domain walls are two-dimensional sheets of energy that separate regions of space with different vacuum energy states. These walls arise when certain symmetries in the universe are broken, leading to distinct regions with differing physical properties. Textures are more complex, three-dimensional defects that represent twists or knots in the fabric of spacetime. Unlike cosmic strings and domain walls, textures are unstable and tend to collapse, releasing energy as they do so. The gravitational effects of cosmic strings, domain walls, and textures could mimic the effects of dark energy by contributing to the overall energy density of the universe and influencing its expansion rate. While individual defects might seem insignificant, their cumulative effect across the vast expanse of the cosmos could be substantial. These defects could have played a significant role in shaping the large-scale structure of the universe, influencing the formation of galaxies and galaxy clusters. The gravitational pull of cosmic strings, for example, could have seeded the formation of early structures by attracting matter to their vicinity. While direct observational evidence for cosmic strings and topological defects remains elusive, scientists continue to search for their signatures in the cosmic microwave background and the distribution of galaxies. Their potential to explain both the missing energy and the formation of cosmic structures makes them a compelling area of research. Having considered the possibility of cosmic defects influencing the universe, the next theory explores an even more abstract concept, the holographic principle. Now, shifting our perspective from cosmic defects to a mind-bending concept, the sixth theory introduces the holographic principle, suggesting that the universe's missing energy might be linked to the idea that our reality is essentially a hologram. This principle proposes that all the information contained within a volume of space can be encoded on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. In this view, what we perceive as a three-dimensional universe might be just a projection of information stored on a distant, two-dimensional boundary. The holographic principle arises from the study of black hole thermodynamics, which reveals a deep connection between gravity, quantum mechanics, and information. Black holes, according to this framework, can be described by their surface area, with the area being proportional to the black hole's entropy or information content. This suggests that the information needed to describe the entire black hole is encoded on its event horizon, the boundary beyond which nothing can escape. Applying this concept to the universe as a whole, some physicists propose that the maximum amount of information or energy that can be contained within a given region of space is limited by its boundary area, not its volume. This could provide an alternative to dark energy by suggesting that the observed energy density of the universe is constrained by the holographic principle. One of the key figures in the development of the holographic principle is physicist Leonard Susskind, who has made significant contributions to our understanding of quantum gravity and string theory. His work has helped to bridge the gap between these theoretical frameworks and the holographic principle, providing a deeper understanding of its implications for cosmology. If the holographic principle holds true for the universe, it would mean that our understanding of space and time needs to be fundamentally revised. It would suggest that the universe is not as it appears and that the true nature of reality lies in the information encoded on a distant boundary. This perspective challenges our conventional notions of energy density and could provide a novel explanation for the missing energy puzzle. Having explored how the holographic principle might redefine our understanding of the universe's energy, the upcoming theory delves into the possibility that the speed of light itself may not be constant. Now, pivoting from the mind-bending implications of holographic universes, the seventh theory considers a radical departure from established physics: variable speed of light. This theory proposes that the speed of light, traditionally considered a universal constant, may not have been constant in the early universe. If the speed of light was significantly higher in the universe's infancy, it could have profound effects on our understanding of energy calculations and cosmological phenomena. The concept of varying constants challenges one of the cornerstones of modern physics, Einstein's theory of relativity, which assumes a constant speed of light. By allowing the speed of light to vary, some cosmological discrepancies, such as the horizon problem, might be resolved. The horizon problem arises from the observation that the cosmic microwave background radiation is remarkably uniform across the entire sky, despite regions of the universe being so far apart that they could not have been in causal contact since the Big Bang. A variable speed of light could allow these distant regions to have interacted in the early universe, thus explaining the observed uniformity. One of the pioneers in exploring the implications of a variable speed of light is Joe Magidjo, a physicist who has extensively researched and advocated for this theory. His work suggests that a faster speed of light in the early universe could explain the universe's large-scale structure and the distribution of galaxies. However, this idea remains controversial within the scientific community, as it requires substantial modifications to our existing physical laws and faces significant challenges in terms of observational evidence and theoretical consistency. The variable speed of light theory offers an intriguing alternative to dark energy by suggesting that our current understanding of fundamental constants may be incomplete. As we consider the possibility of a variable speed of light, our journey through these intriguing theories continues, with the next stop being an exploration into the depths of entropic gravity. Transitioning into another groundbreaking perspective, we arrive at the eighth theory, entropic gravity. This concept, championed by physicist Eric Verland, suggests that gravity isn't a fundamental force at all, but rather an emergent phenomenon arising from entropy and information. In this view, gravity is not a force that is mediated by a particle, but rather a consequence of the statistical behavior of microscopic degrees of freedom. To understand entropic gravity, it's essential to grasp the relationship between entropy and information. Entropy, in this context, refers to the disorder or randomness of a system, while information is related to the number of possible arrangements of that system. Verland's theory proposes that gravity arises from the universe's tendency to maximize its entropy. As objects move and change the information associated with their positions, this creates an entropic force that we perceive as gravity. This apparent gravity could potentially eliminate the need for dark energy, as it offers an alternative explanation for the observed acceleration of the universe's expansion. Instead of attributing this acceleration to a mysterious, repulsive force, entropic gravity suggests it's a natural consequence of the universe's informational dynamics. The theory posits that as the universe evolves and the amount of information associated with it increases, the entropic force driving expansion becomes more pronounced, leading to the observed acceleration. Entropic gravity makes several testable predictions, particularly concerning the behavior of gravity at large scales. One such prediction involves the distribution of dark matter around galaxies. According to Verland, the observed distribution of dark matter can be explained by the entropic effects of ordinary matter, without the need for actual dark matter particles. However, these predictions are subject to ongoing scrutiny and debate within the physics community. While some observations appear to support entropic gravity, others remain challenging to reconcile with the theory. Despite the ongoing debates, entropic gravity represents a fascinating and thought-provoking alternative to the standard cosmological model. By framing gravity as an emergent phenomenon, it challenges our fundamental assumptions about the nature of the universe and opens up new avenues for exploring the enigma of the universe's missing energy. Shifting our focus from gravity to another dimension, the next theory explores possibilities of multiverse leakage. Venturing into the realm of more speculative physics, the ninth theory introduces the possibility of multiverse leakage. This mind-bending idea proposes that our universe isn't a self-contained entity, but rather one of potentially infinitely many universes existing in parallel, and that energy might be seeping from ours into these other universes. The theoretical framework that allows for such energy transfer often involves higher-dimensional brain models derived from string theory. In these models, our universe is confined to a brain, which is like a membrane existing in a higher-dimensional space known as the bulk. Other universes could exist on separate brains, and if these brains are close enough, interactions or exchanges of energy might be possible. The leakage could occur through hypothetical portals or connections that allow energy to tunnel between universes. However, detecting or confirming such leakage presents immense challenges, because these other universes, if they exist, are by definition beyond our direct observation, and any energy transfer would likely be subtle and difficult to distinguish from other cosmological phenomena. Scientists would need to rely on indirect evidence, such as anomalies in the cosmic microwave background or unexpected variations in the universe's expansion rate. Finding definitive proof to this is a challenge. Despite these hurdles, the concept of multiverse leakage continues to captivate physicists and cosmologists, as it offers a radical departure from conventional understandings of the universe and its energy content. It suggests that the missing energy we observe might not be truly missing, but simply residing in another universe forever beyond our reach. As we continue our exploration of the mysteries of the missing energy, the following theory takes us to time-varying dark energy. Switching gears slightly, let's consider the 10th theory, time-varying dark energy. This theory challenges the conventional understanding of dark energy as a constant force, proposing instead that its density changes over the vast expanse of cosmic time. This contrasts sharply with the cosmological constant, which, as the name suggests, assumes dark energy is uniform and unchanging. In models incorporating time-varying dark energy, the observed cosmic acceleration isn't due to a static energy field, but rather a dynamic one. The density of dark energy might have been different in the early universe and could continue to evolve in the future. This variance could explain certain discrepancies in our cosmological models, potentially reconciling theoretical predictions with observational data. One of the key challenges is determining how this variation occurs and what drives it. Some models suggest that scalar fields, similar to the quintessence discussed earlier, could be responsible. These fields would interact with other components of the universe, causing their energy density to change over time. Other approaches invoke modifications to gravity itself, where the strength of gravity weakens or strengthens in response to the universe's expansion. The good news is that future telescopes and experiments might be able to detect shifts in the strength or density of dark energy. By precisely measuring the expansion history of the universe, scientists could look for subtle deviations from what's predicted by the cosmological constant model. Techniques such as weak gravitational lensing, baryon acoustic oscillations, and supernova surveys offer potential avenues for probing the time evolution of dark energy. The implications of confirming time-varying dark energy would be profound, revolutionizing our understanding of the universe's fate and the fundamental laws that govern it. It would open new doors for exploring the nature of dark energy and its role in the cosmos. As our quest to understand the universe's missing energy continues, our next stop involves considering Chaplygin gas. Turning our gaze toward another intriguing possibility, let's explore the 11th theory, Chaplygin gas. This isn't your everyday gas. It's a hypothetical exotic fluid that proposes a rather elegant solution by unifying dark matter and dark energy into a single entity. Imagine a substance that can behave as both, depending on the conditions. The Chaplygin gas is characterized by its bizarre properties, most notably its negative pressure. In ordinary substances, pressure is positive, pushing outward. But in Chaplygin gas, the pressure is negative, exerting an inward pull. This negative pressure contributes to the accelerated expansion of the universe, much like dark energy. At the same time, the gas behaves like dark matter by clumping together under its own gravity, forming the scaffolding upon which galaxies are built. One of the fascinating aspects of Chaplygin gas is its ability to transition from behaving like matter to behaving like energy. In the early universe, when the density was high, Chaplygin gas acted more like regular matter, contributing to structure formation. As the universe expanded and the density decreased, it began to exhibit properties more akin to dark energy, driving the accelerated expansion. However, the Chaplygin gas theory isn't without its critics and observational constraints. One of the main challenges is fitting the model to precise measurements of the cosmic microwave background and the large-scale structure of the universe. Observations place tight constraints on the properties of dark matter and dark energy, and it's not always easy to reconcile these constraints with the behavior of Chaplygin gas. Despite these challenges, the Chaplygin gas remains an active area of research. Scientists continue to refine the model, exploring variations and extensions that might better fit the observational data. It offers a tantalizing possibility that the universe's missing energy isn't missing at all, but simply a manifestation of a single, exotic substance with transformative properties. Keeping with the theme of exotic substances, we now consider the 12th theory, emergent gravity. Building on the theme of innovative approaches, the 12th theory introduces us to the concept of emergent gravity. This theory dares to suggest that what we perceive as spacetime and gravity might not be fundamental forces at all, but rather they could arise from microscopic quantum interactions. Imagine gravity not as a force pulling things together, but as a phenomenon that emerges from the collective behavior of quantum particles. In this view, gravity is similar to temperature or pressure. You wouldn't say that a single atom has a temperature. Instead, temperature emerges from the average motion of many atoms. Similarly, emergent gravity proposes that gravity arises from the collective interactions of fundamental quantum constituents of spacetime. This approach, much like entropic gravity, offers a compelling way to account for the universe's missing energy without needing to invoke new particles or fields. Instead, it suggests that our understanding of gravity itself is incomplete. One of the key successes of emergent gravity is its ability to explain certain aspects of the universe without the need for dark matter or dark energy. By modifying our understanding of gravity at a fundamental level, it can potentially account for the observed rotation curves of galaxies and the accelerated expansion of the universe. However, emergent gravity is not without its unresolved issues. One of the main challenges is developing a complete and consistent theory that can make testable predictions. It's also difficult to reconcile emergent gravity with the standard model of particle physics and general relativity. Despite these challenges, emergent gravity represents a paradigm shift in our understanding of the cosmos. It challenges our most basic assumptions about space, time, and gravity, and offers a new perspective on the nature of the universe. As we continue our exploration of the universe's mysteries, the next stop brings us to the 13th theory, where we will consider supersymmetry's hidden particles. Turning our attention now to another fascinating possibility, the 13th theory suggests that the universe's missing energy could be lurking within undiscovered supersymmetric particles. Supersymmetry, often abbreviated as SUSY, is a theoretical framework in particle physics that proposes a symmetry between bosons and fermions. In simpler terms, SUSY suggests that for every known particle in the standard model, there exists a corresponding heavier superpartner. These superpartners have not yet been observed, but their existence could potentially resolve some of the biggest mysteries in physics. One of the primary reasons physicists are drawn to SUSY theories is their ability to fill gaps in the standard model. For example, SUSY can provide a natural explanation for the hierarchy problem, which is the question of why the Higgs boson is so much lighter than the Planck scale. Additionally, SUSY predicts the unification of the fundamental forces at high energies, which is a long sought-after goal in theoretical physics. But if SUSY is so promising, why haven't we found these superparticles yet? The answer lies in their mass. If superparticles exist, they are likely to be much heavier than the particles we have already discovered. This means that they would require extremely high energy colliders to produce and detect them. Despite decades of searching, experiments at particle colliders, including the Large Hadron Collider, or LHC, at CERN, have not yet found conclusive evidence for SUSY. This could mean that the superparticles are even heavier than initially expected, or that SUSY is not realized in nature in the way we currently understand it. Despite the lack of direct evidence, the LHC continues to play a crucial role in testing SUSY. By colliding protons at incredibly high energies, the LHC can probe the fundamental structure of matter and potentially create new particles. If superparticles do exist within the LHC's energy range, there is still hope that they will be discovered in future experiments. The search for supersymmetry's hidden particles represents a high-stakes quest to unravel the mysteries of dark energy and the fundamental nature of the universe, and now we will move into the next theory. Now, exploring another avenue, the 14th theory connects the mystery of missing energy to an even more fundamental question. Why is there more matter than antimatter in the universe? This imbalance, known as baryon asymmetry, is one of the biggest unsolved problems in cosmology and particle physics. According to our current understanding, the Big Bang should have produced equal amounts of matter and antimatter. However, the universe we observe today is overwhelmingly dominated by matter. This implies that some process must have occurred in the early universe to create an asymmetry between the two. One potential explanation for baryon asymmetry involves CP violation, which stands for charge parity violation. CP symmetry implies that the laws of physics should be the same if we swap a particle with its antiparticle and also mirror the spatial coordinates. Experiments have demonstrated that CP symmetry is violated in weak interactions, but the amount of CP violation observed in the standard model is not sufficient to explain the observed baryon asymmetry. This has led physicists to explore alternative mechanisms such as leptogenesis. Leptogenesis is a theory that proposes that the asymmetry between matter and antimatter was generated through processes involving leptons, which are fundamental particles like electrons and neutrinos. In leptogenesis, heavy, right-handed neutrinos decay in the early universe, producing more leptons than antileptons or vice versa. This lepton asymmetry is then converted into a baryon asymmetry through other interactions. If leptogenesis is indeed the mechanism responsible for the matter-antimatter imbalance, it could also have implications for the missing energy problem. The energy released during the decay of heavy neutrinos could contribute to the overall energy density of the universe, potentially accounting for some of the missing energy. Experiments involving neutrino detectors are crucial for probing this asymmetry. These detectors can measure the properties of neutrinos and antineutrinos with high precision, allowing physicists to search for subtle differences that could provide clues about the origin of baryon asymmetry. Experiments like the Deep Underground Neutrino Experiment, or DUNE, and the Hyper-Kamiokande experiment are designed to study neutrino oscillations and CP violation in the leptonic sector, which could shed light on the connection between matter-antimatter imbalance and the universe's missing energy. As we investigate the mysteries surrounding vacuum metamorphosis, another key theoretical model needs to be assessed. The 15th theory, vacuum metamorphosis, presents an intriguing perspective by suggesting that the universe underwent a phase transition, akin to water freezing into ice, which altered the properties of the vacuum itself and consequently affected cosmic expansion. In physics, a phase transition refers to a transformation of a system from one state to another, accompanied by a change in its physical properties. One familiar example is the change of water from liquid to solid when it freezes. This transition involves a change in the arrangement of water molecules and a release of energy. Similarly, the vacuum, which is the state of lowest possible energy, may have undergone a phase transition in the early universe. This transition could have involved a change in the energy density of the vacuum, which, according to general relativity, would affect the expansion rate of the universe. The idea is that at some point in cosmic history, the vacuum's properties shifted, leading to a sudden increase in its energy density. This increase would then drive the accelerated expansion we observe today, potentially explaining the dominance of dark energy at late times. One way to think about this is to imagine the universe as a container filled with a substance that can exist in different phases, each with different energy densities. In the early universe, this substance might have been in a high-energy phase, causing rapid inflation. Then, as the universe cooled, the substance underwent a phase transition to a lower energy phase, releasing energy and causing a change in the expansion rate. However, the details of this phase transition are still highly speculative. Physicists are exploring various models that could describe how the vacuum's properties might have changed, but there is currently no direct observational evidence to support this theory. Nevertheless, vacuum metamorphosis offers a compelling explanation for dark energy's late-time dominance, suggesting that the universe's expansion is not driven by a mysterious substance, but rather by a fundamental change in the nature of empty space itself. Transitioning from cosmic phase changes in the vacuum, the next theory involves spatial dimensions beyond the familiar three. Shifting our focus from phase transitions, the 16th theory posits that some of the universe's missing energy may be hiding in extra dimensions beyond our familiar three spatial dimensions and one time dimension. This concept builds on the work of physicists like Theodore Kaluza and Oskar Klein, who, in the early 20th century, independently proposed theories involving extraspatial dimensions to unify gravity with electromagnetism. These Kaluza-Klein theories suggest that what we perceive as fundamental forces and particles might actually be manifestations of geometry in higher dimensional space. In these models, the extra dimensions are not directly observable because they are compactified, meaning they are curled up into tiny, subatomic scales. Imagine a garden hose. From a distance, it appears to be a one-dimensional line, but up close, you can see that it also has a circular dimension around its circumference. Similarly, spacetime might have extra dimensions curled up so small we cannot detect them directly. The idea is that energy, including the missing dark energy, could be spread out or diluted across these extra dimensions. This dilution would make the energy appear weaker in our observable three-dimensional space, potentially explaining why we observe a discrepancy between theoretical calculations and experimental observations of dark energy. One compelling aspect of this theory is that it provides a geometrical explanation for the fundamental forces of nature. In Kaluza-Klein theories, electromagnetism arises from the curvature of the extra dimensions, suggesting that gravity and electromagnetism are unified at a fundamental level. However, a significant challenge with extra-dimension theories is that, despite numerous experiments and searches, we have not yet observed direct evidence of these extra dimensions. If they exist, why haven't we detected them? One possibility is that the extra dimensions are simply too small to be probed with current technology. Another is that they interact with our universe in ways that are difficult to detect. Moreover, some models propose the existence of large extra dimensions, which, although not directly visible, could have gravitational effects that might be observable. The ongoing search for these effects continues to be a major area of research in particle physics and cosmology. Considering the possibility of such hidden spatial dimensions, let's now explore if black holes play a role in this missing energy. Now transitioning from the realm of hidden dimensions, the 17th theory we'll explore is the intriguing hypothesis that supermassive black holes may play a significant role in the mystery of dark energy. This idea proposes that black holes, those cosmic behemoths lurking at the centers of galaxies, could be storing or contributing to the vacuum energy that drives the universe's accelerating expansion. The seed of this theory has been planted from the observation that black holes increase in size over time. But where does this mass come from? Recent studies have suggested a surprising link between the growth of black holes and the expansion of the cosmos. Several astrophysicists mentioned an interesting and potentially groundbreaking correlation, indicating that the increase in mass of supermassive black holes aligns with the accelerating expansion of the universe. This has led some researchers to speculate that black holes aren't just passive observers in the cosmic drama, but are active participants, somehow storing or generating vacuum energy. One interesting fact is that supermassive black holes are more prominent in new galaxies compared to the old ones. The basic idea is that as the universe expands, it creates more space, and this expansion might somehow feed energy into the black holes, causing them to grow. This growth, in turn, could contribute to the overall energy density of the universe, effectively acting as a source of dark energy. It's important to note that this theory is still highly speculative, and researchers are actively working to understand the underlying mechanisms. The central question surrounding the black hole dark energy theory is whether the observed correlation between black hole growth and cosmic acceleration is merely a coincidence or if it reflects a deeper, more fundamental connection. Is it possible that the growth of black holes is driven by a currently unknown mechanism related to the expansion of the universe? Or are there other factors at play that we have yet to fully understand? These questions are the subject of ongoing research and debate, with scientists exploring various theoretical models and observational tests to probe the connection between black holes and dark energy. Whether it's a true cause and effect relationship or just a cosmic coincidence remains to be seen, but the possibility that black holes could hold the key to understanding dark energy is an exciting avenue of investigation. Let's move on to another interesting idea of action-like particles and how they might relate to dark energy. Now, turning our attention to the microscopic realm, the 18th theory delves into the world of action-like particles, or ALP as some scientists call them. These are hypothetical particles that some believe could condense into a form of dark energy field, influencing the universe's expansion. Action-like particles are not your everyday kind of matter. They are incredibly light, possibly even lighter than neutrinos, and they interact very weakly with ordinary matter and light. These characteristics make them extremely difficult to detect, but also give them the potential to accumulate and behave in peculiar ways on a cosmic scale. One of the primary reasons physicists are interested in action-like particles is their potential role in solving a puzzle known as the strong CP problem. In particle physics, CP symmetry refers to the combined symmetry of charge conjugation and parity, which essentially means that the laws of physics should remain the same if you swap particles with their antiparticles and reflect their spatial coordinates. However, the strong force, one of the four fundamental forces in nature, appears to violate this CP symmetry in a way that physicists don't fully understand. Actions were initially proposed as a way to restore this symmetry, providing a neat solution to the strong CP problem. Now, how do these action-like particles tie into dark energy? Well, some theories suggest that ALPs could behave like quintessence, the dynamic energy field we discussed earlier. Unlike the cosmological constant, which is a static form of energy, quintessence can change over time and space, affecting the expansion rate of the universe in a dynamic manner. If action-like particles exist and have the right properties, they could form a cosmic field similar to quintessence, contributing to the universe's dark energy budget and driving its accelerated expansion. The search for action-like particles is currently underway in various laboratories around the world. Experiments like the Action Dark Matter E experiment, or ADMX, and the CERN Action Solar Telescope, or CAST, are designed to detect these elusive particles by looking for their interactions with electromagnetic fields. These experiments use powerful magnets and sensitive detectors to try and catch a glimpse of actions converting into photons, or particles of light, under specific conditions. Despite the challenges, the ongoing efforts to find action-like particles represent a crucial step in our quest to understand the nature of dark energy and the fundamental laws of the universe. As we look forward to the next theory, what about if the cosmological constant isn't constant? Transitioning from exotic particles to the very fabric of space itself, the 19th theory puts forward a bold proposition: the cosmological constant isn't truly constant. You might recall that the cosmological constant is the static energy density uniformly filling all of space that Einstein initially introduced, then regretted, and then physicists reintroduced to explain the accelerated expansion of the universe. But what if this constant actually evolves as the universe ages? Quantum field theory offers some intriguing arguments for this so-called running cosmological constant. In quantum field theory, the vacuum or empty space is not really empty but teeming with virtual particles that pop in and out of existence. These virtual particles contribute to the energy density of space, and their effects are what we perceive as the cosmological constant. However, the energy scales at which we measure these quantum fluctuations are vastly different from the cosmological scales at which we observe the effects of dark energy. This discrepancy leads to a problem known as the fine-tuning problem, where the observed value of the cosmological constant is incredibly small compared to what quantum field theory predicts. One potential solution is that the cosmological constant is not fixed but changes, or runs, with the energy scale. As the universe expands and cools, the contributions from these quantum fluctuations might evolve, causing the effective cosmological constant to vary over cosmic time. Now, how does this running cosmological constant fit with observational data? Well, some models suggest that a slowly evolving cosmological constant could explain the observed acceleration of the universe without requiring the existence of exotic dark energy. These models often involve modifications to Einstein's field equations or the introduction of new scalar fields that couple to gravity. While the idea of a running cosmological constant is still speculative, it offers a compelling alternative to the standard cosmological model, and it addresses some of the fundamental issues in theoretical physics. Whether gravity itself might leak into a higher dimensional bulk, setting up the next intriguing concept to explore. Venturing into even more speculative territory, the 20th theory invites us to entertain a truly mind-bending concept: the existence of particles with negative mass. Now, this isn't just about antimatter, which has the same mass as regular matter but opposite charge. We're talking about something far more bizarre: matter that, if you push it, would move toward you instead of away. Imagine a particle that has negative mass. According to Newton's second law, force equals mass times acceleration. If the mass is negative, then the acceleration would be in the opposite direction of the force. So, if you were to push a negative mass particle away from you, it would actually accelerate toward you. It is difficult to imagine, but with the negative mass, this is what happens. How would such negative mass matter interact with ordinary positive mass matter? Well, it would create a repulsive gravitational effect. Normal matter attracts other normal matter through gravity, but negative mass matter would repel normal matter. This repulsion could, in theory, mimic the effects of dark energy, pushing galaxies apart and accelerating the expansion of the universe. However, there are some significant challenges with the idea of negative mass matter. One of the biggest issues is stability. If positive and negative mass particles were to interact, they could theoretically create a runaway effect, where they continuously accelerate away from each other, violating energy conservation. This is because the negative mass particle would gain kinetic energy, while the positive mass particle would lose it, resulting in a net increase in energy. Despite these challenges, the concept of negative mass matter remains an intriguing possibility. So far, no such matter has been detected. It's possible that negative mass matter exists in some hidden sector of the universe beyond our current observational capabilities. Whether or not negative mass matter exists, the search for understanding the universe's missing energy requires scientists to open their minds to possibilities, even those that seem strange. With a discussion about pushing and pulling, the next theory will discuss about holographic dark energy. Now, shifting our perspective from hypothetical particles to the very fabric of reality, let's explore another fascinating idea: holographic dark energy. This theory emerges from the holographic principle, a concept that suggests the information contained within a volume of space can be entirely encoded on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. In the context of the universe's missing energy, holographic dark energy proposes a direct connection between the universe's energy density and its horizon size. The horizon, in this case, refers to the boundary beyond which we cannot observe anything, because light from those distances hasn't had enough time to reach us since the beginning of the universe. The holographic principle suggests that the amount of information, and therefore energy, within this horizon is limited by the horizon's surface area, not its volume. So, how does this limit on total energy provide an alternative to the cosmological constant? The conventional understanding of dark energy, represented by the cosmological constant, assumes a uniform energy density throughout space. However, the holographic principle implies that there is a maximum energy density that the universe can possess, dictated by its size. As the universe expands, its horizon grows, allowing for more energy to be accommodated, but always within the limits set by the holographic principle. This approach offers a potential solution to the puzzle of why dark energy's observed density is so incredibly small compared to theoretical predictions. If the universe's energy is fundamentally tied to its horizon size, it naturally regulates itself, preventing runaway energy densities that would contradict observations. It's not about a mysterious force pushing things apart, but rather a fundamental property of spacetime limiting how much energy can exist within it. The holographic dark energy model presents a compelling framework that connects quantum gravity, cosmology, and information theory, but testing it observationally remains a significant challenge. Future experiments aimed at probing the universe's large-scale structure and the nature of dark energy may offer opportunities to validate or refute this intriguing idea. With information as a key element, the next theory will explore how symmetry-breaking energy, transitioning from the universe's large-scale structure to its fundamental forces. The 22nd theory centers on symmetry-breaking energy. This concept ties the universe's missing energy to phase transitions that occurred in the very early universe, moments when fundamental symmetries were broken. To understand this, think of the early universe as existing in a state of high symmetry, where the fundamental forces of nature, like electromagnetism and the weak force, were unified. As the universe cooled and expanded, it underwent phase transitions similar to water freezing into ice. These transitions broke the symmetries between these forces, causing them to differentiate into the distinct forces we observe today. A prime example of this symmetry breaking is the Higgs mechanism. This mechanism explains how particles acquire mass through their interactions with the Higgs field. When the universe was extremely hot, the Higgs field had a value of 0, and all particles were massless. As the universe cooled, the Higgs field acquired a non-zero value, breaking the symmetry and giving particles mass. Now, the crucial point is that these symmetry-breaking phase transitions release energy, a bit like how energy is released when water freezes. The theory suggests that some residual energy from these transitions might still persist today as dark energy. This residual energy wouldn't be associated with any specific particle or field, but rather with the very structure of spacetime itself. While this theory offers a compelling explanation for the origin of dark energy, it faces challenges in predicting the precise amount of energy that should remain. The energy scales involved in these early universe phase transitions are incredibly high, and it's difficult to calculate how much of that energy would have survived to the present day. Nevertheless, the idea that dark energy is a consequence of symmetry breaking provides a deep connection between particle physics and cosmology. As we continue to uncover the secrets of the early universe, we could discover a piece of evidence pointing to action like particles. Building upon the concept of extra dimensions, the 23rd theory introduces the idea of gravitational leakage into the bulk. This intriguing proposal suggests that gravity might not be confined to our familiar 4 dimensions of space and time, but could instead leak into a higher dimensional space known as the bulk. To visualize this, picture our universe as a membrane or a brain floating within a larger, multi-dimensional space. Gravity, unlike other forces, might be able to propagate into these extra dimensions. If gravity can indeed escape our brain and spread into the bulk, its apparent strength in our universe would be weakened. This weakening of gravity has profound implications for the missing energy problem. If gravity is inherently weaker than we perceive, the observed accelerated expansion of the universe might not require as much dark energy to explain it. In essence, the accelerated expansion we attribute to dark energy could be, at least in part, a consequence of gravity's strength being diluted by its leakage into extra dimensions. The idea of gravitational leakage offers an alternative perspective on the need for dark energy, suggesting that the universe's expansion might be driven by the fundamental properties of gravity itself, rather than by some mysterious energy component. While this theory elegantly addresses the missing energy puzzle, it also raises new questions about the nature of gravity and the structure of spacetime. As we probe the cosmos further, we must consider how the concept of gravity being influenced the universe's entire history as well. Transitioning into another thought-provoking area, the 24th theory challenges our conventional understanding of locality with the concept of non-local gravity. Locality in physics means that an object is only directly influenced by its immediate surroundings. However, non-local gravity suggests that the gravitational effects we observe aren't just due to what's happening now or nearby, but are also influenced by the universe's entire history. In these theories, the usual equations of gravity are modified to include non-local terms. These terms account for the influence of distant regions and past events on the gravitational interactions we observe today. Essentially, the gravitational force between two objects wouldn't solely depend on their current positions and masses, but also on the distribution of matter and energy throughout the universe's past. This approach offers a compelling alternative to dark energy. Instead of invoking a mysterious energy component to explain the accelerated expansion, non-local gravity posits that the expansion is a consequence of the universe's integrated history affecting gravitational interactions. In effect, the non-local terms in the gravitational equations replace the need for dark energy by naturally producing the observed acceleration. Testing non-local gravity theories involves comparing their predictions with cosmological observations. Scientists look for subtle deviations from the predictions of standard gravity and dark energy models in the cosmic microwave background, the large-scale structure of the universe, and the expansion rate at different epochs. While these tests are challenging due to the complexity of the theories, they offer a pathway to either validate or refute the idea that gravity's effects are inherently tied to the universe's full timeline. The next area we will explore involves the concept of unifying dark matter and energy as a single exotic substance. Shifting our focus to a more unified perspective, the 25th theory introduces the concept of a dark fluid. This idea proposes that dark matter and dark energy aren't separate entities but rather different manifestations of a single, exotic substance. Unlike our familiar forms of matter, this dark fluid would possess unique properties that allow it to behave as both dark matter and dark energy, depending on the scale we're observing. The key to understanding dark fluid lies in its equation of state, which describes the relationship between its pressure and density. A peculiar equation of state would enable it to mimic the effects of dark matter on galactic scales, providing the extra gravitational pull needed to explain galaxy rotation curves. Simultaneously, on cosmic scales, it would exert negative pressure, driving the accelerated expansion typically attributed to dark energy. The behavior of dark fluid varies significantly depending on the scale. On smaller galactic scales, its properties would cause it to clump together, acting like dark matter and influencing the motion of stars within galaxies. On larger cosmological scales, it would spread out more uniformly, and its negative pressure would dominate, pushing the universe apart. This dual behavior eliminates the need for two separate dark components, offering a more elegant and unified explanation. One notable comparison is with the Chaplygin gas, which we discussed earlier. Both dark fluid and Chaplygin gas attempt to unify dark matter and dark energy, but they differ in their specific properties and predictions. While Chaplygin gas has a particular equation of state derived from string theory-inspired models, dark fluid theories encompass a broader range of possibilities, allowing for more flexibility in fitting observational data. However, both face challenges in fully reconciling theoretical predictions with the detailed structure of the cosmic microwave background and the large-scale distribution of galaxies. As we continue our journey through the various attempts to resolve the puzzle of the universe's missing energy, we'll now consider how the quantum phenomenon known as the Casimir effect might scale up to cosmic proportions. Transitioning from the realm of theoretical fluids to the intriguing world of quantum mechanics, The 26th theory turns our attention to the Casimir effect on cosmic scales. The Casimir effect, a well-established phenomenon in quantum physics, demonstrates that vacuum fluctuations can create a measurable force. This effect arises when two uncharged conductive plates are placed in a vacuum, resulting in a tiny attractive force between them due to differences in the quantum fluctuations of the electromagnetic field. Scaling up the quantum Casimir effect to cosmic scales involves proposing that similar vacuum fluctuations across the entire universe might collectively generate a repulsive force, driving the observed expansion. According to this idea, the energy density of these vacuum fluctuations would act similarly to dark energy, pushing spacetime apart. The reasoning is that if quantum fluctuations create measurable forces in small, controlled experiments, they could also exert a significant influence on the universe's large-scale structure. However, there are significant feasibility concerns with this theory. The primary challenge lies in the extreme weakness of the Casimir effect. While it's measurable in laboratory settings with precisely engineered conditions, extrapolating it to the vastness of the cosmos requires an enormous amplification factor. Scientists must consider whether the effect could be potent enough to account for the observed accelerated expansion, even if these forces were pervasive throughout the universe. Furthermore, calculations involving vacuum energy often lead to values that are many orders of magnitude larger than what is observationally allowed by the cosmological constant. This discrepancy, known as the cosmological constant problem, poses a major hurdle for any theory that relies on vacuum energy, including the Casimir effect on cosmic scales. Acknowledging these challenges, the theory requires either a yet unknown mechanism to enhance the Casimir effect's influence or a novel interpretation of how vacuum energy contributes to cosmic expansion. And as we consider the quantum behavior of vacuum energy, our exploration takes an even more theoretical turn with the concept of time crystals and their potential role in the universe's energy balance. Shifting our focus from the cosmic echoes of quantum fluctuations, the 27th theory introduces us to an entirely new phase of matter known as time crystals and their possible implications for cosmology. Time crystals, unlike conventional crystals with a spatial lattice structure, possess a periodic structure in time. This means their constituent particles are in constant, repeating motion without requiring energy input, effectively breaking time translation symmetry. In simpler terms, imagine a clock that ticks forever without batteries. That's conceptually similar to a time crystal. They exhibit perpetual motion in their lowest energy state, oscillating between different configurations endlessly. This unique behavior occurs because time crystals maintain order and coherence in time, much like ordinary crystals maintain order in space. Applying time crystals to cosmology involves speculating that their periodic motion could serve as a reservoir of energy, storing or releasing it on cosmic scales and potentially contributing to the observed dark energy. The idea is that a vast network of time crystals distributed throughout the cosmos might subtly influence spacetime through their rhythmic energy fluctuations. These fluctuations could, in theory, exert a pressure that drives the universe's accelerating expansion. However, this theory is highly speculative and faces significant challenges. The primary hurdle is the current lack of evidence for the existence of macroscopic time crystals capable of influencing cosmic phenomena. Time crystals have only been created in highly controlled laboratory settings, and scaling them up to cosmological proportions is a massive leap of imagination. Furthermore, even if macroscopic time crystals did exist, it's unclear how they would interact with spacetime or contribute to dark energy in a manner consistent with observations. The precise mechanisms by which time crystals could store, release, or transfer energy to affect cosmic expansion remain largely unexplored. As we continue our exploration of the universe's missing energy, we now turn our attention to the intricate relationship between information theory and energy, and how this connection might shape our understanding of the cosmos. Building on these abstract concepts, the 28th theory pivots towards an intriguing connection between information theory and energy, reframing our understanding of the universe's energy balance. This perspective suggests that the very fabric of spacetime might be influenced by the energy costs associated with information processing on a cosmic scale. At the heart of this theory lies Landauer's principle, a fundamental concept in information theory. Landauer's principle asserts that erasing one bit of information requires a minimum amount of energy to be dissipated as heat. In other words, information is not free, it has an energetic cost. Now, imagine the universe as a vast computational network constantly processing information. From the formation of galaxies to the interactions of elementary particles, everything can be viewed as a form of computation. If erasing information at the quantum level requires energy, then the sheer amount of information processing occurring in the universe could have significant energetic consequences. The theory proposes that the energy costs of these computations contribute to the expansion of the universe. As the universe processes more and more information, the energy required for these computations adds to the overall energy density, potentially driving the accelerated expansion we observe. This perspective suggests that dark energy is not some mysterious substance, but rather an emergent property of the universe's computational activity. Furthermore, this link between information theory and energy could offer insights into the nature of spacetime itself. Some physicists speculate that spacetime is not a fundamental entity, but rather emerges from the underlying quantum information structure. If that's the case, then the energy costs of information processing could directly shape the geometry and dynamics of spacetime. However, this theory also faces considerable challenges. Firstly, quantifying the total amount of information processing occurring in the universe is an extremely difficult task. Secondly, it's unclear how to precisely link the energy costs of these computations to the observed expansion rate. Thirdly, the very idea that spacetime emerges from quantum information is still highly speculative. With these thought-provoking concepts, we now transition to our 29th theory, loop quantum gravity's corrections. Venturing into another realm of theoretical physics, the 29th theory introduces us to loop quantum gravity's corrections, offering a compelling alternative to string theory as a means to understand dark energy. Loop quantum gravity is an approach that attempts to merge quantum mechanics with general relativity, focusing on quantizing spacetime itself. Unlike string theory, which postulates that fundamental constituents of the universe are one-dimensional strings, loop quantum gravity suggests that spacetime is discrete, composed of finite loops woven together. This quantum spacetime discreteness has profound implications for how we understand gravity at the largest scales. In loop quantum gravity, spacetime is not smooth and continuous as described by Einstein's theory of general relativity, but rather granular at the Planck scale, which is incredibly small, about 10 to the power of -35 meters. These tiny atoms of spacetime are interconnected, forming a network of loops that give rise to the familiar geometry we observe at larger scales. Now, consider the effects of this quantum discreteness on the behavior of gravity. At extremely small scales near the Planck length, the usual laws of general relativity break down and quantum effects become dominant. Loop quantum gravity predicts that these quantum corrections to Einstein's equations could manifest as a repulsive force at very large distances, counteracting the attractive force of gravity. This repulsive force, arising from the quantum nature of spacetime, could potentially explain the accelerated expansion of the universe without the need for dark energy. In this view, dark energy is not a new form of energy, but rather a consequence of the fundamental quantum properties of spacetime itself. One of the key challenges in loop quantum gravity is to derive specific predictions that can be tested observationally. While the theory provides a compelling framework for understanding quantum gravity, it's still a work in progress. physicists are actively working on developing models that link the quantum properties of spacetime to the observed cosmic acceleration. Furthermore, loop quantum gravity has implications for our understanding of black holes and the very early universe. It suggests that black holes have a discrete structure at the Planck scale, potentially resolving the singularity problem predicted by classical general relativity. Similarly, in the early universe, loop quantum gravity may provide insights into the initial conditions that led to the Big Bang. As we approach the final idea, we turn our consideration to the anthropic principle. As we draw near the end of our exploration, the 30th and final theory takes us into somewhat controversial territory, the anthropic principle. This principle suggests that the observed properties of the universe, including the value of dark energy, are not random but are, in some way, biased by the fact that we, as observers, exist. The core idea behind the anthropic principle is that if the value of dark energy were significantly different from what we observe, the universe would either expand too rapidly for galaxies and stars to form, or it would collapse back on itself too quickly for life to emerge. In either scenario, there would be no observers to measure the value of dark energy. Therefore, we find ourselves in a universe where conditions are just right for life because that's the only kind of universe where observers could exist. One of the most intriguing implications of the anthropic principle is the possibility of a multiverse, a vast collection of universes, each with its own set of physical laws and constants. In this view, our universe is just one among countless others, each with a different value for dark energy. Only in those universes where the value of dark energy falls within a narrow range can life arise and observers exist. Now let's consider the scientific validity of the anthropic principle. Critics argue that it lacks predictive power and cannot be tested experimentally. It's more of a philosophical argument than a scientific theory, they say, because it doesn't make specific predictions that can be confirmed or refuted through observation. However, proponents of the anthropic principle argue that it provides a framework for understanding why certain physical constants have the values they do. It suggests that the universe is not arbitrary but is, in some sense, fine-tuned for life. While it may not offer testable predictions in the traditional sense, it raises profound questions about the nature of reality and our place in the cosmos. As we conclude our journey through these varied explanations, one can appreciate the scope of the search. As our cosmic journey draws to a close, let's take a moment to reflect on the remarkable tapestry of theories we've explored, each casting a unique light on the enigma of the universe's missing energy. From the subatomic realm of quantum vacuum energy to the grand scale of extra dimensions, these ideas represent the pinnacle of scientific creativity and human curiosity. Consider the sheer diversity of approaches we've encountered. Quantum vacuum energy proposes that empty space is not truly empty but filled with fluctuating energy, possibly accounting for the missing energy. Quintessence offers a dynamic energy field evolving over time, while modified Newtonian dynamics challenges the very laws of gravity at galactic scales. Phantom energy paints a dramatic scenario of the universe tearing itself apart, and cosmic strings hint at topological defects storing energy from the early cosmos. We've spanned the spectrum from holographic principles suggesting our reality is a projection to variable speed of light theories questioning the constancy of nature's fundamental constants. Entropic gravity suggests gravity itself is an emergent phenomenon, while multiverse leakage imagines our energy bleeding into parallel universes. Time-varying dark energy proposes that dark energy's density changes over time, and the Chaplygin gas attempts to unify dark matter and dark energy into a single exotic fluid. Emergent gravity echoes entropic gravity, suggesting spacetime arises from microscopic interactions, while supersymmetry introduces hidden particles contributing to dark energy. The baryon asymmetry connection ties missing energy to the imbalance between matter and antimatter, and vacuum metamorphosis describes a phase transition altering cosmic expansion. We've even delved into the possibility of black holes storing vacuum energy and action-like particles condensing into dark energy fields. The running cosmological constant suggests the cosmological constant evolves with the universe's age, while negative mass matter turns our understanding of matter on its head. Holographic dark energy connects energy density to the universe's horizon size, and symmetry-breaking energy ties missing energy to phase transitions in the early universe. Gravitational leakage into the bulk proposes gravity weakens due to extra dimensions, while non-local gravity challenges locality, linking gravity's effects to the universe's history. Dark fluid unifies dark matter and energy as a single substance, and the Casimir effect on cosmic scales suggests vacuum fluctuations drive expansion. Time crystals introduce a new phase of matter storing and releasing energy. Information theory links energy to computational costs, and loop quantum gravity offers corrections to gravity's large-scale behavior. Finally, the anthropic principle suggests our existence biases our observations of dark energy. As you ponder these theories, consider which resonates most with you. Does the elegance of quantum fields capture your imagination, or are you drawn to the more radical ideas of extra dimensions and multiverse scenarios? Each theory offers a unique perspective on one of the greatest puzzles in science, and each invites us to think more deeply about the nature of the universe and our place within it. Thank you for joining me on this intellectual odyssey. The quest to understand the missing energy is far from over, so continue to follow the latest discoveries and breakthroughs, and don't forget to subscribe to our channel. Hit the notification bell to stay updated, like this video, and share your thoughts in the comments below. Until next time, keep looking up.